Number 8 on the homework. Let me open up the website or the Canvas shell. And I'm going to do a different share here. So this is my web browser. We're going to go to Canvas. And so module 2, homework. I don't think I ever relabeled it. I think it says module 3 when you open it up. There we go. So number 5, is that correct?
Number 8.
Oh, number 8, I'm sorry. Okay, so there are 2 naturally occurring isotopes of carbon, carbon 63 and carbon 65, which are 69. I got to put my participant list off to the left so I can read this. 2 naturally occurring of chlorine and with a percentage bunches of blah, blah, blah. If copper 1 chloride was subjected to mass spectrometry and individual formula units were ionized and no fragmentation occurred, what would the mass spectrum look like qualitatively? So I repeat the word qualitatively because I don't want you to calculate it. All right. So let's take a look here at this problem. So I'm going to change my share now to my desktop. So hopefully when I get done here, you will now see my desktop. Using one of these Elmos is a pain when you're trying to use your computer for your image, and then also have your participant window open. And then to boot, you're left-handed. It's just like a firestorm. Okay, so I'm now going to open up my web browser so I can read the question. So here they want to know, what does the mass spectrum of copper 1 chloride look like? So for copper, there's copper 63 and there's copper 65. Copper 63 is 69.17%. And copper, oh, that's an 87%, 87%. Copper 65 is, so basically 2/3 and 1/3, agreed? And for chlorine, you've got 35 and you've got 37. And you basically have 76% and 24%. And now that I've written that, I'm going to cross this off and write 69%, and I'm going to write 31%. Because this says qualitatively, which means we don't need to know the precise numbers. Next, we have copper 1 chloride. So copper 1 is a +1, chloride is a -1. So the formula is 1 copper and 1 chloride when we do the switch and simplify. Okay, so here we know that there's 2 atoms in copper 1 chloride, and we want to know what would the mass spectrum look like. Well, you could have a copper 63 and a chlorine 35 with a total mass of 98. So that would be the mass to charge ratio. You could have a copper 35 and a chlorine 37, and you would have a mass to charge ratio of 100. No, that's not right. I wrote the wrong numbers down. 63 and 37, and you'd have 100. Now I'm going to go to the other isotope of copper, which is 65. and you could have a chlorine 35, and this would have a mass of 100. And your spectrometer would not be able to tell the difference between those two. They'd say, oh, they're the same darn thing. And then you could have a copper 65 and a chlorine 37, which would have a mass of 102. Okay, so which one of these four would be the most likely one, most likely? And the answer is, well, since copper 63 is most likely and 35 is most likely, then 65 and 35 is going to be the most likely peak. So I'm going to put this as the largest. And which one's going to be the smallest? Well, the 24 and the 69, or 24 and 31. So this 102 is going to be the smallest. And these two are going to be the mid list. So the one thing we know for darn certain is that this guy is supposed to be bigger than this guy. But the mid list, we don't know if it's going to be taller than the largest or smaller than the largest. And the reason I say taller is because we have to add the two mid lists together because they're both 100s. But we're doing this qualitatively, so that doesn't matter. So we're going to do this. We're going to go 100%, and we're going to say 98 mass to charge, and this is intensity. And we're going to go ahead and just guess that that one's going to be the largest peak. 102 is going to be shorter, and we'll say the mid list may be a little shorter than the tallest. It may be a little taller than the shortest. I don't know. I don't know, but that's kind of the guess. Now, if we wanted to actually figure out which one was the tallest and which one was the shortest, if we look at copper 63 and chlorine 35, the odds of getting that would be the same as 69% times 76%. And basically, we can think of this as being 2/3 of 76 or 3/4 of 69. I'd rather do 2/3 of 76. So this is going to be about 50-ish. And if we look at copper 63 and chlorine 37, this one, 63 and 37, we're looking at 1/4 of 70 or 2/3 of 24. 2/3 of 24 is roughly 16. And you can see when I multiply these, I'm not trying to get 1,600 or something like that. I'm just putting them into numbers that are kind of nice to work with. Copper 65 and chlorine 35, which was also a 100. 65, we got 76 and we got 31. So I can think of this as being 1/3 of 76, or I can think of this as being 3/4 of 31. So I'm going to do 1/3 of 76, which is 25-ish. And for 102, we've got copper 65 and chlorine 37. So we've got 1/4 of 31, which is about 8. So if you look at the numbers, I got 50-ish. I've got this plus this, which is 40-ish. And I've got this, which is 8-ish. You can see if I doubled up everything, this would be 100, this would be 80, and this would be 16. And shoot, I got lucky. I'm pretty close to what it would probably come out to be. And that's the qualitative thing. If I had drawn this peak a little larger than this one, that would be fine too. Because qualitative means you're not supposed to nail it. It means you're supposed to get close. Does that make sense? And then after you get your qualitative, guess what you can do? I'll show you.
Quantitative?
No. So here I'm going to go to my web browser, which I'm going to share with you. And I'm going to go to that www.sis distribution calculator. And guess what I'm going to type into the calculator? I'm going to type in CuCl and see what happens. And they tell me we get 3 peaks, one at 98, one at 100, one at 102. The 98's the taller one. The 100 is shorter, and the 102 is shorter yet. And these are real numbers where my numbers are issues, right? How did my issues turn out compared to the real numbers?
Pretty close.
Pretty close. So an issue is really good when you don't have to calculate numbers. An ish is semi-quant. Semi-quant.
Semi-quant. Got it.
Semi-quant. Semi-quantitative. Because you're working with numbers and multiplying them, but they're not real numbers. They're rounded numbers. So,
got it.
So an ish is a semi-quant. Okay. So does that help you, Sadie, with that one?
Yeah, thank you.
I'm curious, did you kind of come close to this idea at all?
Kind of. I kind of got lost, but I figured it out now.
Okay. So, and does this make sense to you, the explanation?
Yeah.
Okay, even though it's all over the place.
Yeah.
Okay, great. Good question. This is why we have the homework. You're not supposed to necessarily be able to do it. You're supposed to think about it, and then if you can't do it, ask a question. Okay. Does anyone else have a question that they would like to ask? And
Question, Tony.
I'm going to pause you for just one moment. I'm sorry.
You're good.
This is my OCD-ness. Okay, I'm recording. I'm ready for the question now.
Okay. So for the exam that's on the 11th, would you say like the study guide or like something close to that would be the homework problems?
Yeah, I'd say the study guide would be homework problems and problems from the back of the chapter.
Okay.
I would also say that if you want to decide on what things to focus on, because there's so much in every chapter, I would say to focus on the things that I talk about in lecture and to focus on the things that we do in the Q&A that I, say, hey, this is really important.
All right.
So, if you've ever heard me say, and here's a list, and on tests, I like to put lists down. That's not me being teasing. I like to put lists on tests. Now, when I give you 50 lists in 2 chapters, I'm not going to put 50 lists on the test, but you should know those lists that I've given you to be able to describe them. Like, I think I even gave a list of properties of subatomic particles, right? Like symbol, name, location, charge, mass. And I told you for one of those masses, the gram mass, I said, don't know this one, but you should know the other mass. That is, one is 1.00, the other is 1.00, and the last one is 0.
Right.
In atomic mass units. So that's, a nice list to know too. What other lists have we done? Properties of molecular compounds versus ionic compounds. We've done a list of metals versus metalloids. I'm sorry, mostly metals versus non-metals, because metalloids are a mixed bag. What else have we done a list of? You could consider group and period lists, if you will. You should know the list. Where is period 1, 2, 3? Where is period 7? You should know where group 1A, 2A, all the way to 8A is. And for those lists, you should know what 1A is, what 2A is, 7A, and 8A.
Okay.
So, things that I focus on in lecture are things that I tend to put on the exam also. Okay?
Okay, thank you.
All right. No problem. Any other questions there? Okay, with that, nothing being asked, I want to show you how we're going to organize the next 2 Q&As between today and Monday. And I'm going to make sure that I'm sharing what I want to share. Okay, and it's the book. Okay, so here's the book. Can you guys see this little eraser I'm moving around?
Yeah.
Okay,
Yes.
then I'm going to put it off to the side. And now I put it off to the side. Can you see the little pop-ups on the right-hand side of the screen? Looks like a landscape.
No.
You can't see all that, just me, huh? Okay,
Yeah.
then I'm not going to be bothered by it. All right. So what I want us to do is really focus in on what we have remaining in chapter 2. And so here we're going to go to this table of contents. You can see right here, chapter 2 is about atoms, molecules, and ions, right? But we have an even more detailed contents list right here. And I'm going to pull this over so that we can see all of chapter 2 here, or most of it at least. And where is my remote control? Ah, there it is. Okay, so I can't really get all of chapter 2 down here, but I can get most of it. Okay, so let's take a look at, actually, I can't get it all on this page, so we'll just start here. So we've talked about atomic structure. We've talked about
We
atomic
can
number.
only see your web browser, Tony.
Oh, thank you. I thought I was sharing my desktop, so my mistake. Okay, so this is the table of contents. There's 2 content tables. There's the first content table, which just has the chapters, and there's a more detailed one here. So if we take a look at 2.1, we've covered all of these things: atomic structure, number, atomic mass, mass number. We've covered isotopes, determining it, which is basically mass spectrometry, atomic weight. We've talked about how to calculate that. I'm going to zoom in on this a little bit so you can see it a little easier. And I'm going to be moving my book around a bit. That's too much. Okay. 2.2, the periodic table. We've covered periods, groups, metals, metalloids, nonmetals. We even know which elements are the ones that come in pairs, the Hankelbrief. We also know about the ones that are liquids and the ones that are gases, and the rest are solids. Now, molecules, compounds, and formulas, we now know how to name them. And ionic compounds, formulas, and names, we now know how to name them. And so you can see what we have left are these 3 sections here: atoms, molecules, and the mole. And we've actually started a little bit of that, where we were calculating using molar mass. So that's the part where I drew out a symbol of an element, and I said the number at the bottom is the mass of 1 mole of that element, the average element, I should say, the average atom of that element. So we've actually done 2.6, and we want to spend the rest of our time doing chemical analyses, determining compound formulas. And then we also want to use, spend some time on this mass spectrometry. Now, thanks to the question by Sadie, we actually did one of these types of questions about mass spectrometry. So we're going to focus on these last 3 sections for the next 2 lectures. And I just want to make sure that you are aware of that. Okay, so that being said, I'm going to close my book here. And I'm going to grab the problems I have, and I'm going to try and put the scrap paper over here to the left that I'm going to use, and the problems here. And I'm going to try to zoom out, and please remember, if you don't see what it seems to be that I'm talking about, you need to speak out like Alice just did, because I don't know what the hell's, I don't know what's going on sometimes. All right. So we've done a lot of, pardon me?
Oh, sorry. I thought I was on mute. I said you and the rest of us.
Oh,
You're
well,
human. It's okay.
I know I'm supposed to be superhuman because I teach.
Oh, that's right.
Teachers are perfect. Okay, so we've done problems like this, making ions and so forth and so so on. So I don't want to do a whole lot of these problems here that deal with ionic compounds, but we'll do a few because we can do them pretty quickly. So here, what are the charges of ions in cobalt-3 fluoride? Well, cobalt-3 is clearly cobalt with a +3 charge. And fluoride, because it's a non-metal, you figure out its charge by starting in group A and saying 0. Then you go backwards and say -1. And fluorine is in that -1 column. So that would be the ions. And do you remember the switch and simplify? Cobalt gets a 1, but we don't write ones, and fluorine gets a 3. And this one can't be simplified, so we're done. Any questions? So see, some of these are pretty quick. Now, this one is one you need to really be able to do. So this asks you to give the formula and the number of each ion that makes up each of the following. So if we take a look at A, it's got a whole bunch of elements in it. It's got, what, 4 elements in it. What's going on? Well, remember, if you have a metal in it, it's probably ionic, and the metal is going to be the cation. So we should know that the magnesium is the cation. That means the rest of it is the anion. Now, what does this 2 mean? The 2 means that you have 2 of those. Now, if we know this is the cation, and we know it's a +2 charge because it's in group 2A, and you know you have 2 of these, what does the charge on each one have to be so this thing is neutral? -1. So even though we don't recognize this formula, we can actually get it and get the proper charge. Turns out that this is the acetate ion, which I gave you as C2H3O2 -1. They're the same thing. This gives us more information. So B is the same way. You know that aluminum is a metal, so it's going to be the cation, and you know it's a +3. You know that OH has got to be the anion. It's a polyatomic anion, and you can actually figure out the charge from the aluminum. Each one has to be a -1. Now for C, you've got a copper and you've got a carbonate. So you know the copper's got to be the cation, and you know you probably remember there's +1s and +2s, but which one is it? Well, you have to memorize the charge on the carbonate as being -2, and now we can figure out that this copper is +2. So do you see how we go about this? Any questions about how we go about figuring out what the ions are? Normally, you're going to look at the metal. The first metal you see, you're going to say, oh, that is a cation. So this is not a problem given, so I'm going to put G. This is a compound. Get the ions. When you're done, give me a thumbs up or a yes, and then I'll show you the answer.
Gee.
This one I chose because it's got 2 metals in it. Okay, now I'm going to stop you. Here's how you solve it. The first metal's the cation. The rest is the anion. What's the charge on the anion? Well, there's 1 potassium. There's 1 MnO4. The charge has to be -1. So let me give you another one. H. Here is another compound. What are the ions? Take your lesson from the one above.
Same, potassium.
Yep. How about the other ion? What's the formula of the other ion?
The anion is Cr2O7.
And what is the charge on that anion?
Negative.
-2, because there's actually 2 potassiums, right? So that's a
Indeed,
-2. So you see how that works? Whenever you look at these compounds, you're going to look at the first metal, and that's the cation. What is the rest of the formula going to be? The anion. So I'll say that again. You're going to look at the formula. The first metal is the cation. That's it. The first metal is the cation. The rest is an anion. And what type of ions are those called when the rest has more than one element in it? More than one atom, but 2 or more atoms. What do we call that? Polyatomic.
Polyatomic.
Because poly means many, essentially. Actually, poly means more than one.
Mhm.
So if you ever have a child and you name her Polly, it may mean that you think she's a little schizophrenic. Okay, let's move on. So here we have another one that's going to be pretty easy. Platinum +2, right compounds where you have chloride ions and sulfide ions. We won't do that. Here, which of these are correct? Well, we do a little thing here where we look at calcium, see it's a +2. Oxygen is a -2. If we have 2 calciums, that's +4. If we have 1 oxygen, that's -2. That doesn't work because it doesn't add up to 0. So that's how you do a problem like this. Name each of the following compounds. We'll do this one very quickly. Just a couple of them. So here, this is the one where I told you need to figure out the ions first. So you got calcium ion, and you have the acetate ion. So the name of this is calcium acetate. And you'll notice I kind of skipped naming the ions and just said, okay, I'm just going to put the names together and leave ion out of it, calcium acetate. Why is there no Roman numeral on calcium? Because it's a fixed charge cation. We will need a Roman numeral on nickel. So nickel here is going to be a +2 charge, because we know the phosphate is a -3 charge. So this is called nickel 2 phosphate. So nickel, we have to use the parentheses and the charge in Roman numerals because it's one of those that has a variable charge. And just to quickly remind you, if this is the periodic table, and this is boron, and these are the metalloids. To the right here, we have the nonmetals. And to the left, we have the metals. Now, of course, there is one exception here. This is a nonmetal. So this is your periodic table. The fixed charge ones I'm going to do in purple, or in green, apparently. These are all +1. These are all +2. And these are +3. Here we have zinc, which is +2. And here we have silver, which is +1. So those are all of the fixed charge ones. Which cations are variable charged? And that's the rest of them. So the rest of the metals, here in purple, these are the ones that are variable charge, meaning you have to figure out the charge based on the formula of the compound. So that's how we figured out that nickel was a +2, is because of the formula of the compound. Okay, so which of these elements do you have to use parentheses for? The purple ones. It's far easier to remember group 1A, 2A, group 1A is 1, group 2A is 2, 3A is 3, zinc is 2, silver is 1, than to try to remember the charges on all of these guys. All right. So we're going to put that off to the side. And we're going to put off writing formulas off to the side. We did some examples of that. Now, this is a problem that we haven't talked about. And there's a formula in the book that we want to take a look at to be able to do this problem. So this is a property of ionic compounds. Do you remember how I said that ionic compounds have high melting points? Okay, high melting points. And that's because the ions are held together by charge attraction. So they're attracted to each other because of their charges. And this is how you look at that force of attraction. This is the formula. I'm going to write it down, but you don't need to memorize the formula. You need to understand the formula, if you're given it. So let's take a look at ionic compounds and the force of attraction, or the strength of the ionic bond. Ionic compounds, this is my abbreviation for compounds. And we're going to look at the strength of the ionic bond, how well the ions are held together. So the force of attraction, and I'm going to put attraction here. And you may want to write out force instead of an F. It's equal to negative K N, and this is plus E minus N negative E minus all over D squared. And we'll actually make a list here. F is force. K is a constant, so we don't care what it is. N plus is the amount of positive charge. So if you have +1, N plus is +1. And N minus is the amount of negative charge. E is the charge on an electron. And D is the distance between nuclei. Okay, now this number here, this N plus and N minus, it's really the absolute value. And what you're going to end up for every ionic compound is you're going to get some sort of negative X. Negative means they're attracted to one another. Positive means they're repelled. The size of X depends on the values we put here. So for every ionic compound, the E values are exactly the same. The K value is exactly the same. The only thing that differs between ionic compounds is the charge on the cation, the charge on the anion, and the distance between the nuclei. So we definitely want to think about that relationship. The force is proportional to the positive charge. The greater the positive charge, the greater the force. The force is proportional to the negative charge. The greater the negative charge, the greater the force. The force is proportional to 1 over the distance squared. That means if you have a greater distance squared, the ions are farther apart, the force diminishes. This is kind of like magnets. When magnets are close together, what's the force of attraction? It's great. When magnets are farther apart, what is the force of attraction? It diminishes. It's the same for ions. That force diminishes the farther apart they are. So if the nuclei are far apart, that means that the atoms are big, the force of attraction is kind of small. So we want to know this. And the other thing that we want to know is the following. When we look at the size of ions in a period, so lithium, beryllium, actually, let's do the period below that. Let's do potassium, calcium, scandium, all the way over to zinc and gallium. If we want to look at the size of the ions, right here for all these cations, they're about the same. They might differ by 10%, but that's not much. When we look at the ions, they're about the same diameter, okay? Now, why does that matter? Because we use the diameter to figure out how far apart the nuclei are. So if these are two ions, and here's a positive ion, and here's a negative ion, and this is the nucleus, and this is the nucleus, what is that distance? Well, it's this radius of the cation and this radius of the anion added together. So the bigger the diameter of the atom, the bigger the radius, the bigger the distance between the nuclei. So let's consider these two ionic compounds. In which compound are the cation anion attractive forces stronger? So what I'm going to have to do to answer this is go to my periodic table and see that I've got sodium ion here. And next to that, I've got magnesium ion, which is a 2+, and I've got calcium ion, which is a 2+. And then over here, I've got oxygen, which is a 2-, and I've got chlorine down here, which is a -1. Now you might be wondering, so what matters more, charge or distance? And the answer is charge actually makes more of a difference. So if you look at Na and Cl, you've got a +1 and a -1. If you look at CaNO, you've got a +2 and a -2. So which one is going to have a greater force of attraction just due to charge? This one, because you've got 2s instead of 1s. Now, you might also say that if you take a look at these guys, since this guy is going to be larger than that, and one thing I didn't explain, but I'm going to now, is that when you look at sodium versus potassium, potassium is bigger because it has more electrons. So when you look at calcium versus sodium, calcium is bigger. But when you look at oxide versus chloride, oxide is smaller. So this calcium oxide, you've got a big and a small. And for the sodium chloride, you've got a small and a big. So the distances average out to be about the same between the atoms or between the nuclei. So any questions about why calcium oxide would have a greater charge of attraction? You'd say, one, calcium oxide has a greater force of attraction. And the reason why is because calcium is +2 and oxygen is -2, and the charges are greater. Than those of sodium +1 and chloride -1. And I'm actually going to put a +2 and a -2. And furthermore, you would say the distance between the nuclei is probably similar. And that's because you've got a big and a small compared to a small and a big. And we might even do this. That's big compared to that. That's small compared to that. And you see, if this were a question on the exam, which seems to require a description, this is a great description. You're doing it point by point. Now, this would be even better if you wrote a paragraph, but you know what? I don't care about paragraphs. I'd rather see bullet points. And so when I, look for a book in a store and it has a bunch of paragraphs, I like throw it away. I don't want to read that damn thing. I want to find books where it has like a fairy tale. It says dot, Snow White and the Seven Dwarfs. Dot, Snow White was a stepdaughter of an evil queen. Dot, the Seven Dwarfs were Goofy, Daffy, Mickey, Minnie. Clearly, I don't know the dwarfs' names, but you know what I mean. I just like to see the bullet points because I've got the mind that can fill in the blanks. I don't need all the flowery crap. But that's just me. If you wanted to write this out in a paragraph, that would be great too. But this would be sufficient, and we've covered all the things that affect the force of attraction, which are charge and distance. Any questions about that? Okay, then we're going to move on. Actually, the last time I watched Snow White and the Seven Dwarfs, I just remember, I believe it was Dopey. Dopey was beat on viciously by his 6 other dwarfs. And I was like, this can't be a fairy tale. This is just evil. All right. So we talked about naming these guys. We talked about doing molar masses. And this is one of those ones where it's been such a long time that we probably better do it again just to remind you. We did gold. We didn't do helium. I think we did helium. Let's do platinum. So here's platinum. And in our book, you'll find platinum has a 78 at the top, and it has a 195.08 at the bottom. And we are supposed to remember that 195.08 is that 195.08 grams of platinum equals 1 mole of platinum atoms. But we don't usually write atoms there. We write 1 mole of platinum. So if we have 0.063 mole of platinum, and that's an abbreviation for mole, we would multiply by 195.08 grams of platinum over 1 mole of platinum, and we would get our answer. And this particular answer would only have 2 significant figures because of the 0.63. And the way I would estimate this is I would think of it as being 0.63, not 0.063. 0.63 is about 2/3. So 2/3 of this is about 120, maybe 125. Now, since this is actually 10 times bigger than this, the answer shouldn't be 125. It should be more like 12.5. That's what I would expect for the answer. Now, we could also do the reverse. For instance, if we had 4.52 mole of platinum, we could figure out how many grams by multiplying by, oh wait, we just did that. My bad. Let's say that we had 26.4 grams of platinum. We could figure out how many moles by multiplying by 1 mole of platinum over 195.08 grams of platinum. And we would get the moles of platinum. Can everyone see that 24 will go into 195 about 8 times? So this is 1/8, and 1/8 is about 1/12 or 0.12 or something like that. 1/8 is 1/8 is about 1/8, which is about 0.12. Okay, so that's how you use molar mass. Any questions about molar mass? That's something you want to be, you want that to be second nature to you. Okay, let's take a look at a problem like this. You are given 0.1 gram samples of potassium, molybdenum, chromium, and aluminum. So here's potassium on our periodic table. And molybdenum is down here. Potassium is 39.10. Molybdenum is 95.96. Chromium is over here. 52.00. And then we have aluminum, which is over here, which is 26.9998. Okay, so here we have all these different elements. You have 0.1 of each of these. List the samples in order of the amount from smallest to largest. So which one of these is going to have the most moles of atoms? And it's kind of hard to figure out because you have all these numbers and you have all these calculations. But let me reorganize this. And let's say that you have an orange. And then here you have a grapefruit. In general, what weighs more, a grapefruit or an orange? A grapefruit.
Grapefruit.
Okay, and then over here you have a tangerine. In general, what weighs more, a tangerine or an orange?
Orange.
Orange weighs more. And then over here, I'm going to say you don't have a grapefruit, but you have, I don't know, a
Pomelo.
what?
A pomelo.
How do you spell that?
Pom. P-O-M.
You got a melon.
Yellow.
You got a melon.
Okay.
What's bigger, a grapefruit or a melon? A melon. So do you see the melon is the molybdenum, which is the biggest, right? The grapefruit is the chromium, which is the middlest or a middle one. The orange is another middle one, and the tangerine represents the aluminum. Now, if I had 1 pound of each of these, 1 pound, that's something we can, visualize. How many tangerines might I get in 1 pound?
More than any of the others.
Yeah, I might get 3 tangerines. How many oranges? Maybe 2. How many grapefruit? Maybe 1.2. How many melons? Maybe half of a melon at best, right?
Yeah.
So which is going to have the smallest number? The melon. And the melon is the one that's the biggest. So here we would say the molybdenum would be the smallest. The chromium would then be the next smallest, the potassium and the aluminum, and we didn't have to make a single calculation. But now we have to explain, why do we have so few molybdenums and so many aluminums? And the answer is simple. If the atom is smaller, the same mass gives more of them. And that's because the number is proportional to 1 over the mass. The lower the mass, the bigger the number. So you might write something like that down. Or you could do this. 0.1 gram of potassium times 1 mole of potassium over 39.10 grams of potassium is equal to, and you get a number here. And then you do the same thing for chromium. And then you do the same thing for aluminum. And you do the same thing for molybdenum. So you could show 4 calculations and say, okay, here are the numbers, and this number is bigger than this one, and so forth. Or you could do a little explanation, but your reasoning has to be very sound. Any questions about that? They didn't say explain. If I put this on the test, I'd say explain how you came to your conclusion. And if you showed me 4 calculations, that's your explanation. Capiche? Okay,
Yep.
we're going to move on. Okay. A semiconducting material has composed of 52 grams of gallium, 9.5 grams of aluminum, and 112 grams of arsenic. Which has the largest number of atoms in this material? So one way to do it would be to take that 52 grams of gallium, multiply by 1 mole of gallium, and gallium has a molar mass of 69.72. And here this says, which has the larger number of atoms? So it seems like we should calculate atoms, right? I'm not going to. We have 9.5 grams of aluminum times 1 mole of aluminum over 26.98 grams of aluminum. And let's see what each of these answers gives us using my calculator. Can everyone see that the first answer is going to be a little bit less than 1 because it's 50 over 70? But it should be more than a half, right? And so I get 0.75 mole of gallium. And here, 9.5 over 26 is going to be less than half. And I get 0.35 mole of aluminum. Now, I didn't actually calculate atoms, but which one has more atoms? Not a trick question. If you have trouble with this idea, substitute the word dozen. If you have 0.75 dozen gallium or 0.35 dozen aluminum, what do you have more of? Gallium.
Gallium.
So the mole doesn't mean anything other than that there's a whole lot of them. But here it's the same whole lot more. So I don't have to calculate atoms. I can say, well, I got more moles of that. That means I have more atoms. And ultimately, if we do the 112 grams of arsenic times 1 mole of arsenic over 74.92 grams of arsenic, can everyone see that this one is going to be 1.x grams or mole of arsenic? And this one, we could say less than 0.5. And this one, we could say between 0.5 and 1. We don't even need to get the actual numbers. Clearly, 0.5 is less than that, and 1.1 is greater than that. We wouldn't even need to calculate the real numbers. That doesn't mean you don't want to do that on the test. Chances are on the test, you'll want to calculate the real numbers because that's what you're used to doing. But this is how a chemist thinks. They think, why would I calculate that if I don't need to? I'm just asked which one has more, not how many more. Do we understand? You probably want to calculate the numbers because that's what you're used to. We good with that?
Yeah.
Okay, so let's move on. Calculate the molar mass of the following. So we're only going to do one example here. And to calculate the molar mass of the following, here's what I like to do. I like to take the formula and write it out like this. I've got 1 iron. How many carbons do I have? Well, I've got 6 inside parentheses, but I've got 2 of everything in parentheses, so I've actually got 12 carbons. How many hydrogens do we have then? 22. And how many oxygens do we have? 14. Now I multiply the iron times 55.85 because there's 55.85 grams per every 1 mole of iron. So 55.85. And for this calculation, I don't really need units, but I'm going to have 55.85 grams in 1 mole of iron. Carbon, I'm going to have 12 times 12.01. And this is going to be 144.12 grams of carbon. Hydrogen, you're going to use 1.01. And so that's going to be 22.22 grams. And oxygen, you're going to use 16.00. These numbers I'm giving you are the numbers that you're going to find on the periodic table you get on the exam. The same type of number. So 14 times 16 is really tough to do unless I break it apart into 10 times 16 is 160. 4 times 16 is 64. 160 plus 64 is 224. Now this would only have 4 significant figures. This would have 3. This would have 4. And this one would have 4. Because these numbers here are exact. I just counted them. So when I add these all up, I'm going to round to the 10th. So I'm going to estimate this first. You see these first two numbers add up to 200. These second two add up to 246. So I should get what? 446 is my answer. Something like that. Let's see what we get. And I get 446.2 when I round, and that's grams. So to finally write the answer, this is the work, we would write 1 mole of Fe(C6H11O72) is equal to 446.2 grams, and that would be good enough. Although if you wanted to write Fe(C6H11O72), that would be really better, but not necessary. So this would be your answer. This would be your work. Any questions about that? So you could always check your answer, iron 2 gluconate. I'm going to switch my screen. And we'll say iron 2 gluconate molar mass. 448.156. I wonder why they're a little different than what we have. Do we make a mistake somewhere? I don't believe so. I think they screwed up. Take a look at the problem below. Do you see how they have 446? So don't always believe the first thing you see on your Google search. 444.15. Why am I likely to believe this one here below rather than the one above? The one above has no source. The one below looks like it's from a government source where NIH stands for National Institute of Health.gov. Oh my goodness, they probably know what they're talking about. Even this Chem Spider, that doesn't sound like a real source, but you know, maybe it is Chem Spider. Here we have American Elements, probably a private thing, but you know, this is the way we do it. Wikipedia even did okay, right? But usually when you're looking for a source, you want to look for that .gov or .org. Those are usually the ones that are more trustworthy. The ones that say .conspiracy theory, they're the ones you want to stay away from. Because
Indeed.
it's not really .conspiracy theory, it's .con, C-O-N, for
Or
conspiracy.
.alien.
So yes, but stay away from the .cons and do go to the ones that say .org. Okay, I tell you, if they made me in charge of assigning a those dots to things. I would give .con to some of them. All right. So any questions on how to do A, B, or C? Okay,
Can
then I'm
you
gonna
switch your screen back?
Okay, yeah, thank you. See, you're reminding me, and that's what I need. So any questions on how to do an A, B, or C? Recap. I like to make a list. The list shows how many atoms. Then the list shows the mass of one atom. I multiply, then I add. And then finally, I write out the answer. Any questions? Okay, moving on. Calculate the molar mass of each of these hydrated compounds. I'm not going to do one of these problems, but I am going to show you what this means. So this is one of the rare times you're actually going to see a number inside of a formula that's not a subscript. So this means H2C2O4 dot H2O. You know, this would probably be better if we did this. Because that would be more of the standard form of writing these types of things, but it's not how it's done. For these compounds that are called hydrates, you put the number of H2Os with the ion, usually it's an ionic compound, like that. So how many H2Os are in this formula?
2. Oh, 7.
Right. How about this one? How many H2Os here?
Half.
Half. So how many calciums? 1. How many sulfurs? 1. How many hydrogens? 1. How many oxygens? 4.5. So do you understand why there's only one hydrogen? Because you only have half of an H2O. Half of 2 H's is 1 H. What's half of one oxygen? Half.
Yeah.
And then you have 4 over here. So if you wanted to calculate the molar mass of this guy, these are the numbers you'd have to use. Any questions about that? Okay, so we're going to move on from that. 74, refer to the book. Let's take a look at the book very quickly. Actually, you know what? Since it's not written here, I'm just going to skip it. Okay. How many ammonium ions and how many sulfite ions are present in 0.2 mole sample of this? And then how many atoms are contained in this sample? So for this, we're going to have the formula. And let's pretend that we have 1 mole of this. How many moles of ammonium ion do we have? We have 2 moles of ammonium ion. And how many moles of sulfate ion do we have? We have 1 mole of sulfate ion. So we can think of this formula as not just being 1 ammonium sulfate is equal to 2 ammoniums and 1 sulfate. We can actually treat this as a ratio. This is not 2 ammoniums, it's 2 moles of ammonium. So does everyone understand? What I have below and what I have above are the exact same thing. They're just ratios of atoms. And since the formula is counted, these are defined. And can you also see that if we have 1 mole of sulfate ion, that's equal to 1 mole of sulfur, and that's equal to 4 moles of oxygen. Because that's what that's made out of. If you have a whole mole of that, you're going to have a mole of sulfur. And if you have a whole mole of that, you're going to have 4 moles of oxygen. And then we also need to know that if you have 6.022 times 10 to the 23rd atoms, That's 1 mole of atoms. So here, how many ions are present in 0.20 moles? When they say how many ammonium ions, they want to know the number of ions, not the moles of ions. So we're going to take that 0.2 mole of ammonium sulfate. We're going to turn that into moles of ions. And then we're going to turn that into number of ions. And actually, I should say, we're going to turn that into moles of ammonium ions, and then moles number of ammonium ions. So here's how it looks. If we look at this right here, you can see that I've got 2 mole of ammonium ion to 1 mole of ammonium sulfate. Whoops. So there's my first calculation. These cancel, and I now have moles of ammonium ion. This we can also use for ions. So I can say that I have 6.022 times 10 to the 23rd ammonium ions per 1 mole of ammonium. So that's perfectly legitimate. And now we can estimate our answer. What's 2 times 6?
12.
12. What's 0.2 of 12? Well, 0.2 of 10 is 2, so 0.2 of 12 has got to be like 2.2 or something.
2.4.
2.4-ish
2.4 was.
times
yeah.
10 to the 23rd. That's our ish. How many significant figures are we allowed? Well, this is defined by the ratio. This has 4 zig figs and this has 2, so we only get 2 zig figs. So you said 2.4 and you nailed it. So this is the work you'd expect to see for the number of ions. You don't need to show all this stuff, but this is the work you'd expect to see for the number of ammonium ions. How would this change for sulfate ions? Would it be 2 moles of sulfate to 1 mole of ammonium sulfate? Let's see. Nope, it'd be 1 mole of sulfate to 1 mole of ammonium sulfate. Would it be 6.02 times 10 to the 23rd sulfate ions per 1 mole of sulfate? Yes, it would be. So the only thing that would change here would be the NH4s would change to sulfates, and this would be a 1. And you can see if numerically this only changes to a 1, not a 2, then this answer would be half, so it'd be 1.2. Now, I think this is going to be our last problem here. The question is, how many atoms of nitrogen? So I'm going to start with this guy, 0.2 moles of ammonium sulfate. And what we're going to do is we're going to convert that into moles of nitrogen and then into atoms of nitrogen. So if I have 1 mole of ammonium sulfate, how many moles of nitrogen are there here? 2.
2.
And how many moles of hydrogen are there?
8.
8. And how many moles of sulfur are there?
1.
1. And how many moles of oxygen are there?
4.
4. Okay, so you see, I can do this very easily. I'm going to go 0.20 mole of ammonium sulfate times 2 mole of nitrogen per 1 mole of ammonium sulfate, and then times 6.022 times 10 to the 23rd N atoms per 1 mole of N. And do you know what the answer is going to be for this one? Well, we've got this one right above that has the same numbers. So it's going to be 2.4 times 10 to the 23 N atom. Does that make sense? That if you have that many ions, you'll also have that many nitrogen atoms? I
Yep.
think it does. And so based on that, how many hydrogen atoms would you have? 4 times that, right? Okay, but this is how you show the work for those problems. Any questions about that? Okay, so next time we're going to try to work our way through some of these problems a little more quickly. We do want to get to these things that talk about percentage. And we do want to get to these things where we talk about calculating the formula of a compound from percentages. So we want to be able to do those things fairly quickly. Okay. And then some of these problems in the back are basically mixed problems that are based on various topics in the book. All right, so thank you for attending. I believe I recorded the whole thing. Does it say recording somewhere?
Yeah.
Yes.
Yeah.
Okay, so I've recorded, so hopefully in about an hour, I will post this and you can watch it again and again and again because it's much better than anything on TV. Or if you're, have a little insomnia, you can watch this and it'll put you right to sleep. Okay.
I wish it worked that way. It does not always work that way.
Oh,
Yeah, it didn't work for that way for
I
me
have
either.
I have insomnia, and it does not work.
watching this would put me to sleep.
Yeah, no.
All right.
More tired you are, the less it makes sense, and it still doesn't put you to sleep.
Right?
Well, then don't watch it when you're tired.
Just
Watch something that doesn't make sense normally, then when you're tired, maybe it'll make sense. All right.
Sometimes actually it oddly enough makes more sense at 2 o'clock in the morning than it does at 10 o'clock in the morning. It just depends.
Well, I wish you all luck. I'm glad I'm not you trying to learn things online because I would go become a construction worker. Okay. Thanks for attending. I appreciate it.
Thank you.
Hopefully I'll see you all Monday.
Thank you.
Have a good weekend, everybody.
Bye,
right.
guys.
Bye.
do. Bye.